Hello, this is Mrs. Taylor, and I'm going to talk to you about area under curve and how it relates to distance. So the main idea here is if we analyze the accumulation of all the instantaneous changes, we arrive at a total change. So the idea is we have a rate of change, and at any second you have an instantaneous rate of change, and if you can add up all those instantaneous changes, you get an accumulation, which is a total change. And so if we have the velocity of a particle, which is a rate of change, and find the area between the curve and the x-axis, which is what we're referring to up here, this will be the total accumulation of change. In other words, your total accumulation of your changes in velocity, which is the distance traveled. And so to put this into the context of a problem, we have a particle starting at x equals 0, and it moves along the x-axis with the velocity v of t equals t squared for time is greater than or equal to 0. Where is the particle at t equals 3? So the idea is, if I graph my function on this given interval from 0 to 3, and I can calculate the area between the function and the x-axis, that area represents the total distance, the total accumulation of the instantaneous changes. And so right now the one tool we have is our rectangular approximation method. So that's what we're going to do to approximate this area, to approximate where the particle is at t equals 3. And so I think we're going to choose, just for simplicity's sake, our RAM, or the right rectangular approximation method. So what that means is we're going to create rectangles that attach to our curve on the right from 0 to 3. So I'm going to draw those out really quickly. So now we have our rectangles drawn where we are attaching to the curve on the right. And as you can see, it will be an overestimate. That's okay. We're going to make it clear that it's an approximation. And so for a rectangular approximation method, you basically find the area of each rectangle, add them together. And so what we learned in class is if the width of each rectangle is the same, then basically we just find the height, add those together, and multiply by that width. And our height is going to be the y values for each of these x values when I plug them into my velocity formula, or velocity function. So I'm going to create a table and fill that in for t equals 1, 2, and 3, because those are the places where the rectangle is attaching to the curve on the right. So once I fill in my table, when t equals 1, 2, and 3, I would take those, substitute them in to the velocity function, get my y values, and that also gives me the height of each of these rectangles. And the width of each rectangle is 1 unit, so my area will be 1, which is the width of each rectangle, times the heights, which are 1, 4, and 9 added together. So 1 plus 4 plus 9. And 1 plus 4 plus 9 is, that would be 5 plus 4, which is, or excuse me, 5 plus 9, which is 14, times 1 is still 14. So the area under the curve approximately is 14 units squared. So that means that t equals 3 is approximately at x equals 14. Remember, it's moving along the x-axis. So this 14 for this problem represents an x value. And so that's how area under curve is related to distance traveled.